extraction of two-body potentials from scattering amplitudes, and what we found was that at the lowest order, it's very simple that this scattering amplitude after a Fourier transform is in fact the potential, the two-body potential that we're interested in. So that's quite nice, and we had a very nice result. It said that the potential V of P and R, so that's after Fourier transform back into position space. This is equal to let me write it as G over R, and then times a coefficient, let's call it C1, where the C1 is a function of momenta, so M1 square, M2 square, divided by E1, E2, and then 1 minus 2 sigma, where the sigma was equal to P1 dot P2 divided by M1, M2. Okay, and this is valid to all orders in velocity. It's Lorentz invariant, even though it doesn't look that way. Obviously, it doesn't look Lorentz invariant because you have the energies, but that's just from the fact that we're using non-relativistic potentials. So just the idea of using a potential means the Lorentz invariance is not manifest. But it's Lorentz invariant in the sense that this is valid to all orders in velocity. Yeah. Oh, thank you. Indeed, it should be. And this thing, we can give it a name. This is sometimes called one first post-Minkowski. And it's the first term in the G expansion. And this object is the object from which we can derive any conservative physics in any of the situations. We got it from scattering, but now we can apply this to orbital mechanics of closed orbits. And we do that with a Hamiltonian. So H is the square root of P squared plus M1 squared. That's the kinetic energy of one of the particles. P squared plus M2 squared. Remember, we're in the center of mass frame. So the momenta are the same for both particles. M2 squared. Plus the potential, this V of P and R. Maybe if I want, I can give it a label. We'll call this 1 p.m. Call this 1 p.m. 1 p.m. here. Or 1 power of G. It's the order G term. Now, the problem, say we're faced with is going to higher orders of perturbation theory. And things will, of course, get more complicated. And I guess you can ask, how high do we need to go? And I think I told you last time, the answer is as high as possible. The sky's the limit. We are very, very far away from approaching anywhere close to what's needed. If you look at the upcoming experiments, like LISA and so forth, what's actually needed for precision measurements. Obviously, you have to match the precision of the instrument has to be matched by the theory. And we can use this Hamiltonian to derive all sorts of things. For example, a scattering angle. I'm not going to do that for you. I think you can look up in any classical mechanics book how to do a scattering angle. It's pretty much the same way it's done in Newtonian mechanics with the Newtonian potential. You use energy conservation. So, for example, you can get a scattering angle out of this, which, by the way, is encoded in the scattering amplitude. If you look at the scattering amplitude, you go h bar goes to 0. You know what the dominant contribution is going to be. It's going to be the classical limit, and that scattering amplitude will give you the scattering angle. So you can, the information is directly in there, or we can use this Hamiltonian to get the scattering amplitude. The advantage of the Hamiltonian is that once you have a two-body Hamiltonian, now you're talking the right language to speak to our general relativity friends. Everyone will speak Hamiltonians. And so the scattering angle you could get. And I'm not going to go through that. Just look in some textbook. Let me just show you the answer. J is the angular momentum. And then M1, M2, and then 2 sigma square minus 1 divided by the square root of sigma square minus 1. And then plus, there's higher orders. So this is just perturbative. We're just solving it perturbatively. Okay? And any observable can be worked out using this Hamiltonian. As I'm going to comment at the end, life gets quite a bit more complicated when you go to much higher orders of perturbation theory. So when you go 2 more, then fun starts with this comment about once you have the Hamiltonian, you're good to go. It's a little more subtle than that. Okay, and the way you consider higher orders is, well, you consider higher orders, so you start writing down amplitudes. Well, we can do it in terms of diagrams, but of course we mean amplitude. So this is the order G, and then the next order in the two-body Hamiltonian or in the scattering angle, it's encoded in these types of diagrams, this and its partners. I'm just writing down one representative diagram. So there's black hole here, 2 graviton exchange. This is order G squared. And then we can keep on going. There's, say here would be an example. At the next order G cubed. Notice that this contribution is not like electrodynamics because there's no 3-photon interaction. But ignoring these types of diagrams that have 3 graviton interactions, it's the same story in electrodynamics. Yeah. And then, let's see, the next order, we keep on going, there's more and more diagrams, order G to the 4th. Now, those of you who've been in a quantum field theory class may look at this, and you might remember the professor probably said, loops are quantum. Do you know what I'm talking about? Did you hear that? You were taught that, right? Well, that's not entirely true. It's in fact, in some sense, completely wrong. And it's correct in the sense that if you scale the fields in a certain way and you do a certain scaling, then indeed every loop is an order h bar. But that is not the appropriate question. It's not some scaling of h bar according to what looks pretty. It's the scaling of h bar, how to go to the classical limit for the physical problem, right? We're interested in black hole scattering. These are macroscopic, not quantum objects, and we want to know where in the diagrams is encoded the information about the classical scattering. And it turns out that it's in fact completely backwards from what you were taught, that the proper scaling for the question of extracting the classical physics is backwards, that the diagrams, they don't go like h bar, like this one, you say is order h bar, it's in fact 1 over h bar. It's completely opposite. This thing scales like, it's got the opposite scaling. There's more and more powers of h bar in the denominator the higher you go. And you say, okay, where did that come from? Why did that happen? Well, it's not very complicated why that happened, like the origin of this problem. If you have, in the scattering amplitude and the classical limit, we have something like e to the I s classical over h bar. You series expand, you find powers of 1 over h bar. Now, those powers of 1 over h bar, higher and higher powers of 1 over h bar, what's the physical meaning of that? it's iteration. When you expand, when you take this diagram and you repeat it twice, this, and you repeat it twice, there's a 1 over h bar, just from the way it's defined. You repeat it twice, you get 1 over h bar square, 1 over h bar cubed, and so on and so forth. Okay? And those are uninteresting pieces, right? These are sometimes called, this thing is sometimes called, it's like the 1 over, let's say you have 1 over h bar to the 5th. What is that? Sometimes it's called super classical. Why super? I don't know. Anyway, it's a word people use. It's probably not a good word because it makes it sound like it's important. The proper name might be, this is a better name, iteration terms. And these iteration terms are just the repeats of lower orders that appear at higher orders. And they're uninteresting. They're completely uninteresting. When we're interested in the next order of perturbation theory, say we go 1 up, which we will talk about today, when you're interested in 1 higher power of perturbation theory, we are completely uninterested in tree level. The tree level is completely uninteresting because we already know it, right? And we want to ignore or take away this, get rid of this iteration of this. It's already known. So in fact, what you were taught about loops being quantum is exactly backwards. The only piece we're interested to extract the classical higher orders of perturbation theory are the loop pieces. It's the only piece that's interesting. Now, I mean, in fairness, okay, to whatever you learned in your quantum field theory class, depending on the professor, if they were careful, when they said every loop scales like an h bar, it's strictly speaking correct if they were careful with their wording, right? Because if you scale h bars in a certain way, then indeed that's the way it works. Okay, but the physical scaling is different. For example, these legs out here are completely classical. We don't scale them as h bar. These legs here, the gravitons, those we actually do scale like h bar. So there's a difference, right? It depends on the physical situation, right? This momentum here is macroscopic momentum, no h bars. And here, these exchanges of the gravitons, those go like h bar. And that's not, of course, the way the type of scaling that they taught you. Okay. Now, what kind of pieces are we after? So first thing is we can just write down a formal expression with just dimensional analysis of what the potential has to look like. So the classical potential at any order, so n equals 1 to infinity, there'll be some function of momenta and masses and so forth, which I'm suppressing. And then every order perturbation theory, it goes like this. R is, of course, the absolute value of the vector R. And that's our potential. So the pieces that we're interested in the scattering amplitude are simply the Fourier transform of this. If I Fourier transform this, then I know what pieces I want to find in here. And every other piece will be uninteresting. It'll either be one of these iteration, or maybe called the boring piece because it's not interesting, or it will be quantum, which we're also not interested in. Okay. So if we Fourier transform that, then n greater than 1, these are the types of terms we're interested in. Gm q to the 2n. So this is even, the even case. For the odd case, odd n. Then it's q cubed, and then gm q, and then 2m plus 1, and then there's a log q. Okay, so this tells us what we're supposed to fish out of the expression. And the name of the game is to find good methods for extracting exactly these types of pieces out of the scattering amplitudes. Okay? And immediately this tells you some rules. If you have too many powers of Q, there's too many powers of Q, when you do your counting, you'll see that's a term with an H bar. If there's too few powers of Q, it's one of those iteration terms. Right? Okay, so let's now look. By the end of the third lecture, I'll remember I'm supposed to push this button. Okay. So let's look at order G square. So this is the diagram we need, or the types of diagrams. There are, of course, other diagrams. In fact, what we really want is an amplitude. Maybe I'll draw it like this. And let's look at some rules of what we want. Well, the first thing is we know that these lines can't touch. The two matter lines can't touch. It means there has to be a propagator here. Yeah? And there has to be, both places there have to be propagators. If they're propagators, that means that we can look at the residue, meaning the cut. It means we can put this on shell. So, in fact, I will do that. I will put this on shell. Now, later on, we're going to take these gravitons off shell. So, in fact, maybe I shouldn't say that we are putting the gravitons on shell. We are effectively putting them on shell. And what I mean by that is that we're only interested in the residue of the pole. There has to be a propagator here. Otherwise, it's not a long-range force, and therefore, we're not interested in that. And that means we can calculate this on-shell way, and then later on, we're going to go off-shell to extract the potential. Right? The potential is inherently an off-shell object. Okay. And the pieces we're interested in, looking at that counting, so I go over there and I look at the n equals 1, well, the piece I'm interested in, it goes like 1 over q. So this is classical. But remember, there's iteration. So I'm also interested in 1 over q squared. I'm interested in 1 over q squared because I want to track it to make sure that it all cancels out properly, or that I count for the fact it's just an iteration, identify it as an iteration. And anything that goes like q to the 0, I just cross this out. I'm not interested in that. So we have some rules. Rule number 1, place gravitons or I need a 2-particle cut. Let me just phrase it like that. I need a 2-particle cut. And the 2-particle cut separates the 2 blobs so that the matter lines don't touch. The other thing I can do, I can series expand in Q. And in fact, Q is the parameter, this momentum Q, we can actually tag as counting H bars for us. It's basically an H bar expansion that we're doing. And this is the classical piece. one of the nice tricks, once you understand this, that you can do the series expansion, is if we look at the matter propagator. So put some labels here. 1, 2. There's L, and then let's say this one would be P1 minus, let's say this propagator here is P1 minus L square minus M1 square. And I can expand that. So P square, P1 square is M1 square, 2, 3, and 4. So this is 2P1 dot L, and then plus, there's a minus sign, plus L square. Well, what you can do is scale out this external momentum. What you really want to do is replace this with U equals P over M. So it's dimensionless. So L is dimensionful. You leave L as dimensionful. And then you think about the Q counting. And then dimensional analysis, once you've done that, says L is the only parameter that's dimensionful. So therefore, it has to go like Q. So in fact, you realize that this is higher order. So you can series expand this term compared to that. You want to do a series expansion, and you want to rephrase things in terms of matter propagators that are linear. So you're going to series expand in Q, in L. They scale like H bar. You do that series expansion, and you collect order by order in H bar, and you write things in terms of linear propagators. Okay? That's the basic trickery, and then we can start counting, looking at diagrams. Once we've understood this, we can start counting the scaling of the diagrams, different diagrams, how they behave. For example, we can look at a diagram like this, how it behaves, in terms of this Q counting, or H bar counting. By the way, H bar is, of course, 1 in God's units, but we'll make believe that H bar is a good way to count, even though that probably is not the right way to count, since H bar is just some units, right? So you could pick H bar equals 1, and then what do I mean by counting an H bar? But never mind. You guys know what I'm talking about when I say counting an H bar. It's just a parameter that we could be thinking about for keeping track of the types of terms that we're interested in. Okay? And then when you go to human units, then you could put back the H bar. Okay? This diagram, we can look at it, of how it behaves. So first of all, there's a loop integral, d4L. Okay? Then at these vertices, well, the vertices themselves, remember, it's the momentum of this line. So the leading power, the leading behavior, it's order 1. It's not like Q, right? It's the momentum of this line that appears in the vertex. So we ignore that, but there's 2 propagators here. Those guys go like L square and L square, the 2 propagators. Over here, so this is 1 over L square. This propagator, after I've understood I could do the series expansion, this thing goes, the leading behavior is like P dot L, so it's 1 power of L. Okay, and there's another one here. Okay, that's there's another L square, and maybe I could write it as L squared, 1 for each of these propagators. So we find that this thing scales like 1 over Q squared. The 1 over Q squared, that's our iteration. There's an iteration piece in here. That should not surprise you. Right? If you look at this, it looks like an iteration across there. Okay? Now let's look at a triangle diagram. So of course there are contributions that look like this. and we can recount this thing. The count is the same, except I lost one propagator, matter propagator. Right, so this thing scales like d4L. Okay, I have the L squared to the graviton, and then I only have 1 power of L, so this thing goes like 1 over Q. It's this guy. It's triangle integrals. Okay. And now we can look at, let's say, bubble integrals. Right? What happens to that? Let's say a bubble integral like this. Of course, you should be immediately suspicious about this diagram having any relevance in the classical limit, because you might remember you got to have ghosts in there, Faddeev-Popov ghosts. Last I checked, Faddeev-Popov ghosts have nothing to do with classical mechanics. And indeed, you can do your little counting. So we can just, there's a Q square here, right? Or L square here, L at the vertex, because it's only depends on Q or L. So you can just count up this diagram, and you'll find it goes like Q to the 0. So that's quantum. Okay, that's beyond the classical limit, as you might expect. And there's some other diagrams you can worry about. For example, a contribution like this you can worry about. And this one could get you very worried, because if you look at this, it doesn't look like it wants to be something about the classical limit. It's like some kind of self-energy, maybe. And if you do the Q counting, you'll find that indeed it does contribute to the classical limit according to Q counting. But we're going to be interested in potential. So this is already like the first taste of how we think about integration. So at one loop, we can just integrate everything as if though they're Feynman diagrams, the full quantum expression, and we don't have to go through this thing of selecting out pieces. I mean, one loop is simple enough that you can do everything. But at higher loops, you got to be clean, because higher loops, maybe you heard some of the talks like Johannes and Lance, it gets pretty complicated pretty fast, dealing with all sorts of functions that we would not expect to be there in the classical limit. So you need an effective, clean way to throw pieces away that you're not interested in. And here we're interested in the potential. And a key characteristic of the potential is always that the graviton propagators are way off shell, 0 energy. Right? Remember, potentials are instantaneous in time, right? So that means that the energy component of all graviton propagators in what's called the potential region, where we're picking up these, the potential, they're 0. So it means that this thing is instantaneous in time. So the energy integral, just looking at, you could say, the time, this integral in terms of the time, so the propagator, let's say this thing is L, then this propagator, that's right, L squared is L0 squared minus L squared. We're interested only in the potential mode, so forget about that. Keep only this part. That means in terms of, if we Fourier transform to time, it's instantaneous in time. Or we could say we get an integral dE times 1. I mean the E, or the L0, let's write it as L0. Okay, who can tell me what the value of that integral is? It's either infinity or 0. It's one of the two. Well, you think dimensional regularization, there's a whole methodology, method of regions, rules of how you're supposed to deal with this. This, in dimensional regularization, you should not be surprised that this integral is 0. So it goes away. Now, you can also analyze this integral directly. Like, we can do this. It's a one-loop integral. We can work this out. And then you start analyzing it. I guess I'll leave it as homework. Go do that integral. Just inspect it. And then ask the question, do I have this scaling in the final answer, 1 over q? The answer is no. But when we go to higher loops, we need to get much more sophisticated. We can't say, okay, I'm going to do this multi-loop integral, and then I'll extract the answer from that. That's not a happy procedure. You want to quickly isolate the potential modes if you're interested in the potential. Okay? Now, at higher loops, the story is a little more complicated. The conservative piece actually has radiation modes in it. There is some story behind that, some interesting story. It basically has to do with the fact that why that gets more complicated at higher loops is we're doing something very naughty. Where was it? There. Look at that formula. The potential, I write down all orders of perturbation theory, right? And to all orders, and I make it instantaneous in time. This P, I want to put a vector symbol here. This P, there's a P there. That's a P vector. I didn't bring it down far, but that's a P vector. So it's no time component. So this thing is instantaneous in time. Now, you guys can play some bets. What do you think general relativity is going to do if you say, to all orders in perturbation theory, it's instantaneous in time? It's going to complain, and it's going to punish you. And it's going to say, no, it doesn't work that way. What happens is you get non-localities. The Hamiltonian goes non-local at higher orders of perturbation theory. So just a little warning that it's not quite as simple as just say potential modes, you're done, now you have the potential. Higher orders, you also have to consider radiation, and then there's non-localities and so forth. But one thing at a time, at least at low orders of perturbation theory. The amazing thing is these naive ideas work. A potential that is instantaneous in time, in fact, is the correct description of general relativity. Through the third post-Newtonian and the 3 p.m., third post-Minkowskian order, it's all good. Okay. So how do we do? Okay, now we know what we want. Yeah, what we want to do is evaluate. We want to evaluate this. Well, that's a unitarity cut. So the way we're going to do that is exactly the way you expect. We're going to, let's say, the amplitude. That's probably an I want to put in there. ddq 1 on 2 pi to the d. And let me actually draw a little picture on the side here. So let me make this 1 and 2. And this I'll call Q1, and this one I'll call Q2. That's the graviton momenta, so that I have to integrate over. But to get the integrand, I just multiply the 2 tree amplitudes because I'm on top of the residue of the 2 poles. 1 over Q1 squared, Q2 squared. So let me put back the poles. So it's not actually a cut, but it's the thing that gives, you cut this thing, you get the correct cut. Compton. Okay, 1, 4, Q1, Q2 is helicities, H1 and H2. I have to sum over that. I'm sticking a sum over the states. I have to sum over the states. Okay, then another Compton. By the Compton, I just mean it has 2 scalars, 2 gravitons. It's the tree amplitude. And then 2, 3. minus Q1 minus H1. So that's would be the helicities or the states of the graviton H2. And this is all treated on shell. This is gauge invariant. Okay. Now, how are we going to do this? Well, first what we should do is go back to QED. The gravitational calculation turns out to be essentially identical to the QED calculation. In fact, it turns out you can recycle it. It's basically the same algebra and exactly the same. So let's first look at QED. So instead of gravitons, we do photons. Okay, so here's the Compton. 1. So we'll take the bottom of the diagram. So let me just keep those labels, Q2. Okay, we have a second diagram. I have to apologize that I'm writing down Feynman diagrams, but this is a pretty dopey problem. It's just a 4-point with scalars. You can just write it down without any effort. Okay, it's just a 4-point tree. So if you are allergic to Feynman diagrams, be my guest, do it some other way. It's okay. Okay, so this thing is so simple. We're basically done. We just write it down. We just write down the diagrams, and then we write down the amplitude, and we're finished. So it's 2I. There's a Q square. There's charges here. We'll put this charges sitting there. And the diagrams are epsilon of Q1. So it's this one. So I'm writing down first that diagram. Dot P1. Epsilon of Q2. Dot P4. I'm using on-shell conditions to simplify. Remember, the vertex was a difference of momenta, this minus that. But I'm making use of some on-shell cleaning up. Okay, P1 dot Q1 plus epsilon of Q1 dot P4, epsilon of Q2 dot P1 plus epsilon of Q1 dot epsilon of Q2. So that's for the contact term, the Siegel diagram. And there we have it. Okay. So first thing, of course, the Compton is gauge invariant. Is gauge invariant, of course. It has the property, the way this thing is set up, it has the property that if I take epsilon of Q1 and I send it to Q1, then this MQED Compton, it goes to 0. And the same with the other one. Therefore, see, my state sum is very happy. Right? Remember the state sum? We have to sum, so we have to sum these photons across that cut. Wherever the cut is, we have to sum it across the cut. Right? We're doing this problem. There's the one Compton, this photon, and then we have to sum over states. Okay, so that state sum, the sum of, let's say, epsilon Q1, okay, the complex conjugate, or also I could take the opposite momentum. This thing, as you remember, minus, there's a mu and a nu. Minus eta mu nu, and then it was plus P dot, Q, we call it Q. Q1 dot, I don't know if you'd call it, let me call it R for reference. This is mu and nu plus q1 nu r mu divided by q1 dot r. Okay. And this term, it's immediately zero because I'm going to get a q dotted against either this side or that side, and then it'll just vanish. So this I can just throw away. Goes to zero. It drops out immediately. So essentially, we've gone in some sense to Feynman gauge because the propagator, the photon propagators now just have the eta mu nu. So that's all very nice. Oh, I lost, yes. So there should be, indeed, I lost a propagator. Thanks. Okay. Anyway, for homework, you can verify everything I said here. That you can just drop that. In fact, more homework. Let me just leave homework. I can't do all the work. You have to do some of the work. The homework is now use this. So you have the amplitudes. You have them on both sides. You got to do, relabel for the upper side. Use this formula and put it all together. Put together. And let's see what we get on the other side. What you find is that this amplitude, so we'll call it Q1 square, Q2 square, right? There's charges on both sides. The upper charge doesn't have to be the same as the lower charge, so let's make it Q1 square, Q2 square. That's equal to some coefficient. I'll call it CB. But CB it's the coefficient of the box integral. So this is an integral. Right? This is not a Feynman diagram. It's just an integral, a scalar integral. I just put in the propagators and I integrate. So this is an integral. So this is an integral. Okay, then I can have a cross box. There's a cross box. So let's call this the XB cross box. I can have a triangle integral. And it's like an upward one. I can have a triangle integral, a downward one. So maybe we'll call this guy this symbol and, just a name for it. Okay, and what we find is that the answer is a linear combination of these integrals plus some other integrals we're not interested in. The bubble integral. Remember, bubble integral is quantum, so we're not interested in that. So the answer in the classical limit is just a combination of some coefficients, xb, I xb, plus c delta, I delta, plus c the other way around, the upside down triangle, I triangle, plus some quantum. So this is bubble stuff. Anyway, ignore that. Bubble, tadpole. And this is algebraic, where these coefficients, let me tell you what those coefficients are. CB, let's say put a QED, that's equal to the same coefficient for the cross box, and that's equal to C m1 square m2 square. I'll define C in a second. Sigma square. Oh, am I too low? Might be too low. Okay. Where the C is equal to minus a half, is equal to 4q1 q2. course, there's squares. So it just has a dependence on the sigma. Sigma is equal to P1 dot P2 divided by M1, M2. So these are the coefficients of the box and the cross box. And the triangle, let me write QED, that's equal to minus 1/2 C M1 square. And not surprisingly, if you flip it over, the masses flip. QED is equal to minus 1/2 C M2 square. Okay. Now, you might notice something, that this coefficient is the same as that coefficient. And you say, okay, maybe it's a simple case and that's an accident. But indeed, this is not an accident. This is actually something crucial of how the classical limit works. That these diagrams, they come in pairs where it's ordered one way and then this leg flips to the other side. And it's that combination which makes the classical limit work. And now, when you go to higher orders in perturbation theory, this is always true, that things come in pairs like this, or in multiples, maybe it's a whole bunch of them that are needed at higher loops, that basically you take this leg and it wanders in all possible ways, and you'll find the coefficients match. Well, not exactly. I mean, it gets very complicated, it's very entangled, and it depends on how you write things. But nevertheless, what you observe at this low orders, in fact, is the key for understanding how it works at higher orders, what combinations you need to get the classical limit to come out. And maybe just, I'm doing on time, I think I should actually write down what the integral is, one of these integrals, instead of it being some abstract thing. I should at least write down one integral. Sure. It's possible. Yeah, it's possible. It certainly, at higher orders, it certainly gets very complicated to see this. In fact, the way we work is we assume this is true, and then you check it afterwards. That actually does come out with the right combinations. But it's certainly, well, this was understood by George Sturman, as you can imagine. That probably is not a surprise to you. Okay, we like to call it Sturman combinations. Okay, where was I? I wanted to write down the integral. Oh, yes, there's room here. So let me just write down one integral so you can see what I mean by an integral. By an integral, I mean an integral. So this would be the box integral. So the box integral is exactly what you think it is. ID integral ddl L minus Q squared. Q is equal to P2 plus P3. So it's just an ordinary Feynman integral. P2 minus L squared minus M1 squared. Now, what I wrote here is the fully covariant integral. So at this level that I'm working, we haven't done any series expansion yet in terms of expanding in Q or L, like the orders of H bar. This statement up there, that statement, that algebraically, you just do a little bit of algebra, cleaning this up, you'll find that it's a linear combination of those integrals. That's what these fully covariant integrals. Then, of course, at the next step, I can start series expanding and then picking out the classical pieces I want. Or maybe if I'm on one loop, I can just do the integrals directly. Okay, so this is the QED answer right there, using those Comptons. So how are we going to do gravity? Let's have a look at gravity. So gravity, we do exactly the same way. And we're going to, well, we're not only going to do it exactly the same way, but we're going to use the QED answer to give us the gravity answer. It's kind of cool. I need my eraser. So you remember in Henrik Johansson's lectures, he was talking about the double copy, the Kawhi-Llewellyn tie relations. So let's just use the Kawhi-Llewellyn tie relations. So KLT, it says that M gravity, and then 1, 2, 3, 4. And these legs here, normally it's written in terms of gravitons, but if you want scalars, you can go to higher dimensions, do a dimensional reduction, you get scalars out of it. So this relation I'm writing down actually holds exactly for our amplitudes without any modification. 2 K1 dot K2, and then not QED. Remember, it's Yang-Mills. The Kawhi-Llewellyn tie relations are non-abelian gauge theory. 1, 2, 3, 4, and then Yang-Mills 1, 2, 4, 3. And remember, these are color-ordered amplitudes. That means that the legs of these amplitudes follow an ordering, right? They follow, if you write down the Feynman diagrams of these amplitudes, here, 1, 2, 3, 4. It has to follow that ordering. Those are the only diagrams that are allowed, the ones that follow the ordering. We look at this and we say, let's see, what are the diagrams? So we would, I guess we would write down these diagrams, 1, 2, 3, 4. And you look at this and you say, well, actually, if I write them as the full set of diagrams, of course, another one, 1, 3, 2, 4. So this would be the color the complete set of diagrams. And you say, oh, look, this is not in QED, right? Because it's a non-abelian vertex. But I want you to notice something. See, 1, 2, 4, 3. What diagram is that? Right? 1, 2, 4, 3 is the diagram, but I'm going to write it in this order. 1, 2, 4, 3. Or this amplitude here, 1, I guess you can have the 2 over here, then the 4 over here, and then the 3 over here. See, there's no non-abelian vertex in this one. There's no non-abelian vertex. You say, wait a second, this is QED. This one's already QED. Let me replace that. QED. Okay? Now I look at the other one. I say, oh, but wait a second, this guy's, it's the wrong ordering. It's got the non-abelian guy in there. But I happen to know, maybe Henrik mentioned something like a BCJ amplitude relation, which you can find in textbooks from 1985, so maybe it shouldn't be called that. So in Green, Schwartz, and Witten, you can find a relationship between the color-ordered amplitudes like this. A 1, 2, 3, 4 is equal to 2 K2 dot K4 divided by 2 K3 K2 dot K3, and then A 1, 2, 4, 3. So you can use relationships between color-ordered amplitudes, converting one ordering to another ordering by multiplying and dividing by appropriate propagators, inverse propagators. And then you notice, oh, this guy's QED. So this is really cool. So the gravity one, in fact, we can fix this. The gravity one is actually a square of QED. Kind of a cool little fact. So this thing we can rewrite. There's a 2K1 dot K2. There's the 2K2 dot K4. And then 2K3 dot K2 dot K3. And then I have a QED. And then maybe I'll write it in this ordering. Although for QED, it doesn't matter what the ordering is. So in fact, it's the same algebra. So to get the gravitational case, we just follow the same steps. It is a little more complicated because you can't algebraically reduce to those scalar integrals. You have to do a little bit of work. There's some integration reduction you have to do to the basis of integrals. It's because you get some numerator factors with loop momentum, and then you have to do some work. The lazy way to do it is you download a computer program that does the reduction to the basis of integrals that we were talking about, the integrand that you get out of this procedure. I prefer Fire. That's my favorite program. But there are many other programs you can use to do that. Or you could just say, heck, it's one loop, I know how to integrate, so you could do it some other way. That's okay too. And let me just quote the answer, and then I think I will be at the end of my time. So now we have, following exactly the same procedure. I'm almost done. Now we have in GR, and we're looking at the classical limit because we're going to be throwing away things like the bubble integrals. We have GR, the box integral, CGR, the cross box integral, plus then the triangle integrals. Okay, I'm making GR triangle. Triangle integral, the upside down triangle, C GR, the upside down triangle, and then plus quantum, and let me just write down the answer, and then we will call it quits. C, the GR, the B. Indeed, as expected, there's a reason for this. It always happens. There's the cross box. They're identical coefficients. And there's a constant, let's call it CGR, and then 4 m1 square m2 square times 2 sigma square minus 1 squared. If you recognize this is the square of the tree, that is correct. It's iteration. So it's square of the tree, iteration. Exactly what these boxes are doing. And then we have the triangle integral. That's where the meat is. Those are the pieces that control the correction to the two-body potential. I'll write down what the CGR is in a second. Minus 3, and then 5 sigma square minus 1, m1 square, and then the other one is the same except GR except I have to just put in an M2 square. No surprise, it's upside down, so you have to swap the masses. And this CGR, a constant is 64 pi squared g squared m1 squared m2 squared. Okay, so that's the answer. Almost identical to QED. And maybe the punchline is you might be surprised that the logic of how we're doing all this and the algebra, the details of the theory, are identical between the gauge theory and gravity. So you can go home and ponder the question of, but I thought that gravity was different, a geometric theory. It's, right, the whole formulation is fundamentally different. And I guess what I'm telling you is no, it's not. It's just like QED on steroids. It's a much more, complicated theory, but it's very, very similar to QED. Definitely very much like Yang-Mills theory. Okay, so I'll finish up the lecture this afternoon.
Thank you, sir. Questions?
Nice.
I'm curious, although this is a slightly gauge-dependent question, whether you get a contribution from the triangle graph, which has a propagator, graviton propagator connecting, the three graviton vertex.
The three.
Where you, it was like the triangle you wrote down, but this guy.
Oh yeah.
Can that one?
Yes, it's in there.
Okay.
The fun part is it all got hidden in the KLT, and the place it got hidden, it's in here. See this guy? The propagator is there.
Okay.
Yeah.
So despite the fact that you wrote it as QED, it's
Indeed.
really there. Yeah.
Maybe
because when I power counted it, I got that it contributed, but I might have.
Yes.
Yeah, you didn't show it earlier, but I thought it power counted the same as the one with the contact.
Absolutely,
Thanks.
it does contribute. And there's little trickery where I made it into QED. It's only going to work at this order. So this is just a cute little trick. But nevertheless, the principle that it's like Yang-Mills, that one holds generally. All of gravity, we can follow these types of procedures, KLT, to always express these unitarity cuts, like this one, those guys. We can always re-express them in terms of Yang-Mills objects, always gauge theory. Here, it was just a cute little trick, which, in fact, as Lance points out, it kind of hides the physics, because it made it look like I did not have the non-abelian vertex, which would be very weird, or the graviton vertex, did not have this graviton vertex in there. But that's actually not correct. It is in there. It's just that through the KLT trickery, we could rewrite things in such a way that it's expressed in terms of QED, but that graviton propagator, this guy, is definitely in the expression. Yeah.
I was wondering, now we started with spinless black holes, right, in the beginning?
Yes.
If we go now to spinning black holes, can we do something similar, and what exactly would change on the diagram level?
Yes, you can do something similar. And this has actually been done, written in terms of field theory operators. Basically, you have to write down couplings that include spin coupling to gravitons. You have to write that down. The way you do that is you just write down every single gauge invariant operator you can think of a certain mass counting, and then you march on. And there's we have a paper with Roybon and Andres Luna, and it explains how to do that. Now, we, in all fairness, the way we did it is field theory, and it's been done before, of course, by the general relativists. Endless numbers of papers, 500 papers on the subject, and that's done in a different way. world line formalism using a world line and then coupling to spin carried by this world line. It is a popular way, and pretty much we just copy the way they do it. There's a one-to-one observation. You can look at their operators and map it to our operators, more or less.
Okay, thank you.
In fact, there's a whole, not just spin, but every property that you could come up with for the either black holes or neutron stars. It can be approached from the point of view of effective field theory. You have gravitons, and they couple to this object, and then you just start writing down a list of operators. Those operators correspond to what astrophysicists would also be doing. Let's say you're interested in some neutron star. How does it couple? How does the spin of the black hole, of the neutron star, couple to the gravitational field? You need some phenomenological parameters. We call them Wilson coefficients. They're just coefficients of operators. So there's a whole systematic way of dealing with any property. You name spin, tidal effects, and I'm sure you can even do some dissipation effects in the, that there must be a way of doing that in the field theory, although the last one no one has worked out.
Can you explain more about why the superclassical piece in your amplitude doesn't give you a superclassical potential?
This you have to wait to the next lecture. So at the amplitude level, indeed, the thing looks like there's something in there that you don't want. This, we don't want this superclassical thing. It's like I called it the boring piece, right? So you have to get rid of this. And the way that we are going to get rid of this, or at least the way I'm going to show you, is through effective field theory. We'll write an effective field theory for the potential, like the way you would write some kind of a non-relativistic effective field theory, except we're going to do it all orders of velocity, consistent with Lorentz invariance, and you match that to this thing. Both will have iterations. The iterations will match. We will say we're uninterested, subtract them off from both sides, and then the leftover piece will be the potential we'll be interested in. So there's a procedure that still has to be done. So indeed, as you point out, this amplitude, the way it works right now, we can't read off a potential. There are ways of reading off, for example, scattering angle can be read off, because in the classical limit, it's basically you can pick up an iconal phase. That iconal phase can be used to determine what the scattering angle is. So the information is encoded in this amplitude. The question is how to extract it in a good way. And that requires one more lecture.
Thank you.
So is the equality between C box and C cross box also related to the BCJ relation? Because these two coefficients should be related to the tree amplitude.
Probably not. Only in very simple cases. So yes, it is related, but only at the 4-point. So in these relatively simple cases, you can use BCJ relations to understand exactly why the thing comes out with the same coefficient. However, if you go to like a 5-point blob, you go to, let's find it, like this one. Let's say we're looking at, some higher, let's say at higher loops, there's something like this that you're looking at, right? And there's some 5-point trees that you need. Then those relations are much more complicated. And let's just say the clarity of how this comes out, the fact that always things come in pairs becomes much more obscure. So it's just an accident of 4 points that it's very visible exactly in these BCJ relations why swapping things over didn't matter. But higher points, it's more complicated. Okay. Nevertheless, it's true.
I don't see any other questions, so time for a coffee break. Thank you, Zvi.